Okay, thank you. And thanks for organizing the conference in this difficult time. It's very nice that people, conference organizers actually did all this work. I just hope that one fallout from the pandemic won't be that we'll be giving 25-minute talks at all conferences in the future. Let me talk about something that has been discussed a little bit yesterday. And this is, by the way, most of the main results here are going to be joint work with Tarek El-Kindi. And so this is about mixing and universals mixers in particular. So we have a transport equation here with U being a passive flow, and we are trying to mix as well as we can. So find U that gives us the best mixing. And rho is some scalar that's bounded, and I'll assume it to be, for convenience, means 0. And it's some concentration of something, and the flow that we are looking for has to be incompressible. And we have some initial datum, and then we are asking what flow to pick so that after a while, this scalar will be mixed very well. The domain doesn't really matter too much. So I'll just pick it to be the square or cube in several dimensions. Whatever I tell you will work in any dimension. And it can be just with boundaries, or it can be the torus. And the reason why this cube here is in red is because this doesn't get mentioned that much, but actually, if I should paraphrase John, that, well, torus is not real, get over it. So the torus really doesn't exist as a, actual domain in our three-dimensional space. So if you know something about mixing on the torus, and somebody gives you a bucket and asks you to mix something in it, so maybe that stuff from the torus may not be that useful in that actual application. So that's why I like, whenever possible, to include cubes or squares or bounded domains in in this result. So in that case, of course, the flow is going to be tangential at the boundary. And again, so the goal is to get or figure out some flows, come up with some flows, construct some flows that give us the best mixing. And so this is just a very quick slide on what happens if you do have diffusion. Of course, here we have no diffusion. If you do have diffusion, you can look at measures of mixing that are based on the LP norms, but you can't do that if you don't have diffusion, so you need something else. So I will just skip this slide quickly, and if anybody wants to see it, then of course it will be on the video. What are the measures of mixing? So one of them we already saw yesterday is what I call the functional mixing scale. And this is just think of F that being our rho, being bounded and having L infinity norm 1. So this here and this here is just 1. And so then this functional mixing scale is just the h minus 1/2 norm squared maybe. And there can be any h minus s norm actually, but there is a good reason to pick h minus 1/2, and I'll mention that on the next slide. And so then there is a second one, which is sort of Bressan's mixing scale, which is sort of a geometric mixing scale. And it's a little bit different. So take scale epsilon and take all balls of radius epsilon and ask whether the average of our F, which is mean 0, is less than or equal kappa on each of these balls. And kappa is some kind of number that you pick. So for example, you could pick it to be 1/3. And in that case, if F, for example, takes just values 1 and -1, so let's say black and white, then what you want is in every ball of scale or of size epsilon, you want at least 1/3 of the stuff to be white and at least 1/3 to be black. And then you consider that mixed well enough to this scale epsilon. And so this comes originally from Bressan, who considered precisely this case in 2 dimensions with kappa equal 1/3, but you can pick kappa something else, whatever you like. And so in this scale, you really want to be mixed everywhere in the domain, but certain deviations from perfect mixing are tolerated, and basically kappa tells you how much do you tolerate? On the other hand, this functional mixing scale, you don't look individually at small areas, you sort of average out how well you are mixed, but then you don't tolerate that much these deviations, and you can see it on this relationship, which comes from a paper by Matthew Message and Petzold, where the functional mixing scale is, or the norm is equivalent to the mix norm, which averages this degree of mixedness on small balls. So you square that and then you average it over the domain and also average it over the radius of the ball, and then take 1/2. Okay, I forgot to say that the mixing scale for the geometric mixing scale is the smallest epsilon, for which all these averages are less than equal kappa. So however low you can go with this epsilon. And for functional is just this norm. Okay, and so as I said, I would mention, why do I do h minus 1/2? Well, h minus 1 is maybe more standard, but actually all the results with h minus 1/2 that I will talk about will also hold for h minus 1. And h minus 1/2 has this advantage that it is related to this mix norm by Matthew Message and Petzold. And that's a very convenient way to track this functional mixing scale through the mix norm. Okay, so what do we mean by mixing by a flow? Well, we start with some initial datum. Maybe a standard one is you take your square or your cube and make 1/2 of it black and 1/2 of it white, just left half black, right half white, and then start mixing. So then the characteristic function of 1/2 minus characteristic function of the other half, that's the initial datum, and start mixing, and then ask if you have some flow and your solution of the transport equation is kappa mix. For some kappa you pick, let's say kappa is just 1/3, kappa mix to scale epsilon at time t. So you say the flow kappa mix is the initial datum to scale epsilon in time t. And there is this conjecture of Bressan, which actually is almost 20 years old, and I don't know whether I should say it's surprising that it's still unsolved. Maybe he should have offered some money for it. But the conjecture says the following, that if we put some kind of constraint, and specifically this constraint on the flow, of course we need to put some constraint, otherwise we could mix very quickly. But if we put this constraint, so L1 norm of the gradient of the flow is uniformly bounded in time, then you take this initial datum, and if you want to mix it to scale epsilon in time t, then the time has to be at least logarithmic in epsilon. Okay, and if you turn it around, what that means that the scale to which you can mix this flow, this initial datum with flow that satisfies this constraint, that time cannot decrease faster than exponentially. And he talked about the geometric mixing scale, but of course you can state it similarly for the functional mixing scale. Okay, so cannot decrease faster than exponentially, you cannot mix better than exponentially. That's the conjecture, and it is still open. But if you replace the constraint, instead of L1, you put an LP here for any p greater than 1, then this was resolved 5 years later by Kripa and Delelis, who indeed show that then the conjecture holds. And so this was for the geometric mixing scale, and then you can use that result to translate it into the functional mixing scale result that was done by Size and by Iyer, Kiselev, and Shu a few years later. And maybe just a note here that why one would want constraints like this. Well, for example, if U solves the stationary Navier-Stokes, stationary force Navier-Stokes, then this L2 norm is precisely the energy you have to pump in to keep it going. Okay, so this is a reasonable constraint from that point of view as well. Let me mention a few results here that have been obtained recently when it comes to this exponential mixing. So there was a paper of myself with Yao and another paper with, of Alberti, Kripa, and Mazzucato. These are the years of when they were published. They were written earlier. And so with Yao, we show that if you take any initial datum, then you can find a flow that indeed does mix it exponentially, and the flow satisfies the constraint from the previous slide, this constraint, for any p between 1 and this number, which is golden ratio plus 1. So that includes, for example, p equal 2 as well. Okay, but the flow depends on the initial datum. So you are given an initial datum, and then you come up with a flow that does the mixing for that initial datum for you. And in fact, we can also handle p greater than this number, but then the mixing is not exponential, it's a little bit slower. So in the exponent, you have t to some power, which is greater than 3/4, but is not 1. And Alberti, Kripa, and Mazzucato, they were able to show exponential mixing for all p, but only for special initial data. So basically for this one that I mentioned previously, the one that Bressan talked about. So half torus is black, half torus is white. And this was done on the torus, and what we did was also on a square. But both of these were only in 2 dimensions. And in addition to that, they, as I said, the flows depend on the initial data. And moreover, the flows gained more finer and finer structure. And as a result, while these constraints are okay to get exponential decrease of the mixing scale, if you want to make a constraint like that, where s is not 1 anymore, but it's greater than 1, then actually that exponential decay becomes just algebraic. So that's because those flows gain fine structures. And so there's a natural question: can you relax all these restrictions? So can you upgrade this to several dimensions? Can you make the flow to be a universal mixer, meaning that it doesn't depend on the initial datum? And can you also replace the constraint by a stronger constraint, so a constraint like this, but with s greater than 1? And so here is our result regarding these questions. Again, this is joint work with Tarek. And so for any dimension greater or equal to, there is indeed a universal mixer with that satisfies a constraint from the previous slide. It's a flow that's time periodic on both. You can construct it both on the torus and on the cube, the dimensional cube. Obviously satisfies the right boundary condition, is incompressible. And so it's in this WSP with uniform bound for p in the same interval as in my paper with Yao, and s less than this number. And this means that if you take p equal to 1, which gives you the largest range for s, you get s less than 1 plus square root of 5 over 2, so the golden ratio. And so this flow is a universal mixer in the sense that if you take any initial datum for your transport equation, then its mixing scale converges to 0 as time converges to infinity. But there is no rate. However, if your initial datum has at least some regularity, so it is in some h sigma for any sigma greater than 0, then in fact, the mixing scale does decay exponentially, and the rate only depends on the sigma. And so we call that that flow being an almost universal exponential mixer, because it mixes reasonably nice, not too nice, but just a little bit nice data. And so both these results are in both geometric and functional sense. So whether you look at the functional mixing scale or geometric mixing scale, both of those you get the same result. Okay, so I should mention that what do I mean by this universal mixing? So for each individual initial datum, we get exponential decay, and the rate again only depends on the regularity of the datum. However, the time when this decay starts will depend on the initial datum. And that's sort of clear because you can take some specially constructed initial datum for your flow, which is a fixed flow for your universal mixer. So you can take initial datum such that the flow after time 1,000,000 just turns it into something very badly mixed. Okay, you can construct such initial datum, and therefore you have to wait 1,000,000 before the mixing actually starts for that particular initial datum. So the time depends on the time when the mixing starts depends on the initial datum, but not the rate. Okay, and for the geometric mixing result, the kappa, which is the error you are allowing in how well you want everything to be mixed, that exponential rate does not depend on it. Okay, now obviously you might ask, however, how about just the exponential universal mixer? So all initial data are mixed exponentially quickly, and that is not possible. And so that's the second result here. Any universal mixer that you have cannot be universal exponential mixer, only almost universal, but even more than that, it cannot have any mixing rate. So whether you want it exponential or some slower rate, it just cannot have it. That works for all initial data. And the idea of this is that, well, you can just construct an initial datum that does what I just described. So after a very long time, sort of obtains, after mixing with that particular mixer, obtains some area which is not well mixed. And then you can construct a datum that does this at a very sparse sequence of time. And the areas or the regions you obtain at those sequences converge to zero in size, but very, very slowly. And therefore, you can beat any kind of rate by just constructing your initial datum to beat that rate. But of course, that will mean that your datum won't be smooth, won't have any degree of smoothness. Okay, let me make a few remarks here. So universal mixing and even exponential mixing is well known in the dynamical systems community. There are many examples of maps that do that. However, when you actually want to find examples of flows, you have to work a little bit. So you can find maps, but you need to find flows that realize those maps. That's not so easy. So there are these Anosov flows that are flows on tangent bundles of some compact Riemannian manifolds, and as a result, they are at least three-dimensional manifolds, and they have negative curvature. So obviously, they are not embedded in three-dimensional space. So those examples are known. When you want some examples on flat spaces, so for example, on the torus, you have some low regularity exponential mixing flows. These Anosov flows, they are time independent. These are time dependent. And for example, you can realize the well-known Arnold's CAD map as a one-period flow map of a time periodic flow with a very simple structure. But this flow is not continuous. It's only BV. Okay, so, and again, it's only on the torus. So as far as I know, there are, at least I'm not aware of there being a more smoother examples. So, and if you want even W11 or better regularity or even continuous, there were no other examples that we were aware of. And if you want examples on actually a square or a cube rather than torus, then also we were not aware of any other examples like that. So these would be the first examples of sort of universal in a sense. So what I mean by that, almost universal exponential mixers. Okay, so let me, let's see. Do I have about, what is it, 6-7 minutes?
Yeah, 6 or 7 minutes. That would be great.
So, so let me just say a little bit about how you construct these flows. So there is a basic building block, and from that everything flows. And this is in 2 dimensions, and then you can upgrade this construction to more dimensions. But basically, this basic building block is the main component of it, and it's just a flow that rotates a square 90 degrees in time 1. Okay, so you want to come up with an incompressible flow like that. And well, what you probably can think of is cellular flow, right? So cellular flow has a stream function, which is just the product of these two signs. Right? The problem, of course, is, well, there are two problems. So the first problem is that the cellular flow doesn't rotate every streamline at the same rate. So you won't rotate the whole square at once by 90 degrees. And the second problem is that the boundary takes infinite amount of time to go around. Okay, so the first problem you can remedy by just multiplying your flow. So how do you get your flow? You take the grad perp of the stream function, so multiply that by t, which depends on the level set, and it's just the integral of 1 over the velocity on that level set. And so that means it speeds up the slower level sets and it slows down the faster ones. And you put 1/4 because you want to rotate only 1/4 of the square. So you want to rotate only 1/4 of a circle. So so you can remedy that, but the problem with that is that this t becomes infinity on the boundary. And so that makes your flow not very regular. So what you do instead is you divide the stream function by some of these signs to some alpha, where alpha is between 0 and 1. And then, of course, that messes up this stream function near the boundary. So the larger alpha, the less regular this stream function is, and therefore your original flow. But then it improves the regularity of the t a little bit. The t is still going to be not great near the boundary, but it's going to be better if alpha is larger. And so you take this flow here, and then you ask for what alpha you get the best regularity. And it turns out you can do a little bit of computation, and you find out that alpha 3 minus square root of 5 gives you the best regularity. And as a result, the flow you get, which again is this sort of cellular-like flow with streamlines sped up a little bit, each of them sped up its own rate, and it turns then the square 90 degrees. So you get that this flow is indeed going to be in all those WSP spaces that the theorem requires. And of course, those spaces are in the theorem because this flow belongs to those. Okay, and so you can do that by estimating the gradient of the Hessian of the flow. And so this all works very well only on the square, but not on the torus. The reason for that is that the flow on, let's say, this right side goes up, and then on the left side goes down. So if you're on the torus, you have a discontinuity in this flow along this whole line and similar along this line. So you need to do something else. You need to adjust this construction, and I don't have the time to talk about it, but you can do it by splitting the torus into 4 pieces and then do some massaging of that. But anyway, let me just stick with the case of the square. So you have this flow, and that you know exactly what it does at time 1. It just rotates the square by 1/4 by 90 degrees. You need to work a little bit more to have a good estimate on what happens between time 0 and time 1, and that's not so easy because the flow is only Hölder continuous. It's not Lipschitz, obviously, and so the flow maps could in principle be disconnected, but actually, these are discontinuous, but actually they aren't, and we can show that the flow maps are uniformly Hölder continuous in time. Anyway, and so now what does this flow do for you? So here's what you do with it. You split your square into 2 bits, and you apply this flow in each of these bits separately and rotate each of these rectangles by 90 degrees. So this one to the left and this one to the right. And of course, by rotating rectangles, I mean that you also squish them in the process so that you remain within a square. So, so each of the rectangles is preserved by this rotation. And when you do that, after you do that, you take the whole square and rotate it to the left by 90 degrees. And what you get is this. So this 2, the second rectangle gets squished from the top to bottom and stretched from the left to right, and then ends up on the top. And this one also gets squished and stretched and ends up at the bottom. And so that's the time 1 map of this flow, which is made of this composition of these simple flows that rotate rectangles. And the time-on map has a name. It's called a folded-Baker's map. And the nice thing that it does is that when you take a dyadic square inside this big square, so what happens to it is exactly the same that happens to these two rectangles. It gets squished by a factor of 2 from top to bottom and gets stretched from left to right by a factor of 2. And so the square turns into a narrow, longer rectangle. And then you apply repeatedly this map, and the rectangle becomes narrower and narrower and longer and longer. And eventually it covers the whole square from left to right, and then it ends up being cut into 2 and turns into 2 strips, and then into 4 strips and 8 strips, etc. And so it's possible, thanks to the explicit nature of this transformation, to track exactly what happens to that rectangle. And you find out that if you apply certain number of times, let's say 2k times the map to a small dyadic square that starts of size 2 to minus k, then it will be of size 2 to minus k times, so it will become a rectangle of size, sorry, I think I got something wrong. Oh, yes. Its intersection with any other dyadic square is going to be a little rectangle of size 2 to minus k times 2 to minus 3k. So that means every little dyadic square gets splashed all over the domain and really uniformly. And if you look at any dyadic square, then all other dyadic squares transform into it just the same amount of their original substance. So that means if you have a nice, at least a little bit smooth initial datum, you can imagine that means that gets splashed regularly all over the domain, all over the square. And as a result, you get very nice mixing. And so with that, that's all. Thank you.